Hello all, welcome again. This is a session as per the request from many subscribers about kernel synchronization and interrupt handling. So please subscribe to our channel if you did not subscribe for more videos onto us, and please press bell icon and like and share button to support us. So in this we'll be learning about timers, interrupts, bottom halves, kernel synchronization, and a glimpse. So timers, interrupts, and bottom halves, and kernel synchronization. Let's get on to the timers. What are all timers we have to look into in a real-time operating systems um, for an embedded systems? One is real-time clock, stamp counter, programmable interval timer, PIT, that is PIT, RTC, TSC, and PIT, CPU local timer, high precision timer, ACPI management timer. So, what do we need interrupts? Why do we need interrupts? Interrupts is to getting information from hardware when it's needed, processing data when it's needed, that is software interrupts. One solution would be polling overhead through unnecessary checks. Better solution, interrupts. Work is only done when needed. So what is an hardware interrupt? We just looked into getting information from hardware when it's needed. That means we should know what is an hardware interrupt. Electrical signal asynchronously emitted by a hardware device. Each device is mapped to an interrupt request line processed by an interrupt controller, forces the CPU to handle the interrupt. So dealing with hardware interrupts, kernel gets interrupted by the CPU. Each IRQ line has interrupt handlers. One is C function, implements a specific function type executed in its own context, that is interrupt context. So writing our own interrupt handler will consist of two things. One is function prototype and then registering the handler at IRQ. So this is how we write a function prototype. Here see static IRQ return underscore T intr underscore handler int with an arguments interrupt request int integer IRQ void pointer device ID struct pt underscore registration regs pointer regs. So how to register it at the IRQ is first go with the declarations like this: IRQ return underscore T handler, and we'll have two variables, that is integer, three variables, three arguments we are passing: integer comma void and struct pt underscore regs as we discussed in the function prototype. Unsigned long IRQ flags and const char pointer dev name, device name, void pointer device ID. This is how we register the handler at the IRQ, by just declaring this. So what all kinds of interrupt handlers available? One is SA interrupt, and then is SA sample random, and SA SHIRQ. So the key features of SA interrupt are short execution time, not interruptible. SA sample random source for kernel entropy pool, and SA shirk will consist of multiple handlers possible. Handler detects the which device emitted the interrupt. Every register handler is checked for the emitting device. So we spoke about an interrupt context, right? Interrupt context is not associated to any process running in the main. Running process gets dumped to kernel memory, no ability to sleep, and its own stack, that is one page. Simple rules are be quick and short, only use the stack if absolutely necessary. So I repeat, interrupt context will have these features which is not associated to any process. Running process gets dumped to kernel memory, no ability to sleep, its own stack. It will have its own stack, that is one page. Simple rules for it is it should be quick and short. Only use the stack if absolutely necessary. Okay. Managing the interrupts is also important, right? So we have four things to be considered in managing interrupts. One is enabling or disabling interrupts, and second one is disabling specific interrupts, status of interrupts, that is activation context, etc. Interrupt Fourth one is interrupt statistics. So local IRQ enable, local IRQ disable will enable or disable interrupts. Disabling specific interrupts, this is disable dot IRQ unsigned int IRQ. We are passing that particular IRQ number. Status of interrupts activation context. One is IRQ disabled interrupt or it is enabled. Is that interrupt going on? So interrupt statistics will be in slash proc slash interrupts. Okay, let's look at an overview of interrupt handling. So suppose a hardware here, a keyboard generates an interrupt. Okay, let's look at this. Generates an interrupt, and interrupt controller will be communicating to the processor. Processor interrupts the kernel and does this IRQ interrupt request. Is there an interrupt handler on this line? Is the first thing which it will check. If yes, handler handle IRQ event. So it will handle this particular method will handle the IRQ event. You can write your own names for the methods. Okay, just for an understanding, I'm going with an general method name or a standard method name. So if there is there is an interrupt handler on this line. If this condition is no or a false, it returns from INTR. Then run all interrupt handlers on this line, or it will return to the kernel code that was interrupted. So I press a key something, it generates an interrupt. Interrupt controller sends that signal to the processor, and processor interrupts the kernel which is running right now. So then it will do the IRQ, and it checks is there an interrupt handler on this line. If it is there, handle IRQ events will be called and run all the interrupts. If not, so it will return from INTR, okay, and return to the kernel code that was interrupted, where it was interrupted. So why do we need bottom halves? You heard about bottom halves and top halves, right? So the interrupt handler needs to be finished fast. All processes on the CPU are blocked by interrupt, only used for time critical tasks and arrival confirmations. Bottom halves are used for data processing as well. Interrupts are enabled while executing a bottom half. So types of bottom halves. There are four types of bottom halves. One is depreciated types, soft IRQ, tasklets, and work queues. So this is how it is. Depreciated type, soft IRQ, tasklets, and work queues. So in depreciated type, there are two things. One is bottom half interface. Second one is task queues. So what is soft IRQ? Soft IRQ is statically allocated at compile time. Maximum number of 32 soft IRQs can be run at a time. It depends upon your processor and so in general, most of the cases it would be 32 soft IRQ implemented as a structure. That means which points to a function to run. Soft IRQ handler gets a pointer to the structure. Just look at this method void soft IRQ underscore handler, which will have an argument struct type soft IRQ action underscore action, and we have pointer points to a function to run, right? So needs to be marked for execution in a bit mask. So for each and every soft IRQ, you need to mark for execution in a bit mask. Gets executed by a looper over the soft IRQ vector array. So the usage, now we learned what is soft IRQ and how it is implemented. The usage is for assigning a priority index, registering the handler, marking it for execution. So this is how it is done. Open soft IRQ, raise soft IRQ, handler gets executed by next to do soft IRQ run. What is a tasklet? Tasklets are based on soft IRQs implemented as tasklet struct. State field manages its execution status organized in a linked list tasklet structures gets executed in the do soft IRQ cycle. Writing our own tasklet is one is to declare the tasklet whether it is statically implemented or dynamically implement a tasklet handler. So we'll write a function prototype for a tasklet handler and then schedule the tasklet. These three things are important. How to do that is this is how it was done. Declare a tasklet, name function data. This takes argument name function data. Dynamically tasklet underscore init. So it takes three arguments t, tasklet handler, and device dev. Next, implement a tasklet handler. So function prototype goes like this: void underscore tasklet underscore handler unsigned long data, schedule the tasklet by tasklet underscore schedule, which takes the ampersand your tasklet, address of your tasklet. So next we'll be discussing on work queues. Work queues, they are executed by their own kernel thread, executed in process context. Okay, organized in linked list of work queue structure. So what is the first work and what is the second work, third work? That means first work will consider will have a pointer which is denoting to the next link of the work. That means it is organized in the linked list of work queue. So usage of work queues are declare work queue at runtime and implement handler, schedule the work queue just like tasklets. So it will also have statically or dynamically declaring it, implement it and schedule it just like. So statically if you are declaring it, declare underscore work, and it will take three arguments called void, sorry, name, void function pointer, void, and void data, and dynamically initialize work, which takes an argument like struct work underscore struct pointer work, void function pointer void pointer void data. How to implement the handler? Just work underscore handler, which takes an void pointer data. Schedule the work queue is by just passing to the method address of work. Which bottom half should I choose? Whether I have to choose, we have seen like soft IRQ, tasklet, and work queue. So, on what basis would we choose this bottom halves? Soft IRQ is highest priority operations, short execution time, and thread safe. On these things, we choose an soft IRQ. So, just if it is a short execution time, doesn't need to be thread safe, then we go with an tasklet. See, if we have a big operations, IO operations, for example, which doesn't need to be a thread slave, then we'll go with an work queues. I repeat, when we have high priority operations, short execution time, and when we require a thread safety of the thread, then we'll go with soft IRQ. So we just require short execution and thread need not to be safe, then we'll go with an tasklet. But if the operations are really big, something like IO, input output, doesn't need any thread safety, then we'll go with an work queue. This is how we choose the bottom half. What are synchronization mechanisms used? Functions and structures provided by the kernel. So prohibit race condition in share memory. So if you guys are not aware of race conditions, just go through our channel in the playlist RTOS. We discussed about it. So these are all the synchronization mechanism. Why are these mechanisms necessary? The kernel is not running serially. If the kernel is not running serially, most kernels use preemption and multi-core processor system. Kernel control paths are interleaving. Paths are interleaving. In this situations, we need a mechanism to control that, right? So what are all the synchronization primitives required? There are few elementary mechanisms to synchronize programs, that is per CPU variables. Local interrupt disabling, local soft IRQ disabling, optimization and memory barriers, atomic operations. Then comes the real task like spin locks, semaphores and completions, SCQ, sequence locks, and read copy update, that is RCU. So all these mechanisms to synchronize programs should be taken care per CPU variables. Local interrupt disabling, so local soft IRQ disabling, optimization and memory barriers, atomic operations, spin locks, semaphores, and semaphores and completions, sequence locks, and RCU. So, where are these things not needed? Before we take a closer look at the mechanisms, there are cases in which no synchronization mechanisms are required or needed. So where are they them not needed? One is interrupts, soft IRQs, and tasklets, unique structures in the tasklets. Interrupts disable their IRQ lines, cannot be nested or interleaved by deferrable functions or non-blocking and non-preemptible. Next, soft IRQs and tasklets, they can be interleaved on their CPU and are non-blocking and non-preemptible. And unique structures in tasklets, they need no synchronization because they can only be executed with one instance on all CPUs. These are all where our synchronization mechanisms are not required. We have a single core and multi-core, right? You know what is a single core I'm talking about. Per CPU variable means simplest way to make sure that no other CPU can corrupt the memory with interrupt handlers, soft IRQs and tasklet, race condition secure. Interrupt and soft IRQ disabling is required, can be used to make interrupt handlers thread secure. Optimization memory barriers is one more challenge. Instructions which affect at the compiler, they avoid optimization and reorganization of the instructions in the compiler. Optimization barriers assure that the assembly instructions remain in the same order, and memory barriers ensure that the instructions before the barrier are finished when the barrier is reached. Instructions which affect the compiler, they avoid optimization and reorganization of instructions in the compiler. Optimization barriers assure that the assembly instructions remain in the same order, and memory barriers ensure that the instructions before the barrier are finished when the barrier is reached. So we'll have multi-cores as well. In that, we need to look at atomic operations. Atomic operations appear to be instantaneous to the hardware. You need to know about spin locks. We have a separate session on the spin locks. Make sure that the readers and writers don't get into the conflict accessing a resource is what the spin lock is. Make sure that the readers and writers don't get into conflicts accessing a resource. There are different types of spin locks. One is simple spin lock and read write spin lock. The waiting process spin, that is, they execute a tiny instruction loop to check whether the lock has yet been released. So we discussed most of the synchronizations. Next is semaphores and completions. Waiting processes are put to sleep and awakened when they are at the first place of the waiting queue and the lock is free. Next is SEQ locks, like spin lock, but with privileges to the writers. The readers have to check after the reading if the byte that uh, they read is valid or not. This is sequence locks. So RCU, use of a pointer, and thus only available for data on the heap. This synchronization is only available for the data on the heap. So the big kernel lock forces the processor to allow only one process in kernel space. I hope we discussed most of the kernel synchronization and interrupt handling on the higher note. Important things required. If you want to dig deeper, write to us, and please subscribe to our channel. If you did not subscribe, please press like button and share to support us to make more videos onto it. Hope you like this session. Thank you.